Hello everyone, welcome you all for the session on design of flexible pavement using ISC 37 2018. Myself Ashok Kumar, Assistant Professor, Department of Civil Engineering, Walchand, Institute of Technology, Solapur. The today's learning outcome of the session, at the end of the session, students will be able to design the flexible pavement as per the IRC 37 guidelines. Before we go into the design of flexible pavement, we'll understand the different the layers of flexible pavement. Right from the subgrade, below the subgrade, we have embankment also. Depending upon the topography, there may be embankment of the infinite thickness. So next we have subbase, that is granular subbase, that is a drainage layer. The thickness in the range of 100 mm to 300 mm. And atop of the subbase, we have a base course. It may be your wet mix macadam. The thickness lies in the between 100 to 300 mm. And binder course, that is dense bituminous macadam of 50 to 100 mm. And final layer, that is the wearing surface, or the final layer is a surface course, that is a bituminous concrete, maybe in the range of 25 to 50 mm. So now, based on the property of a subgrade and other properties, we are going to design the thickness of subbase, base, binder course and surface course. So what are the design parameters we should consider for the flexible pavement design? That is subgrade strength, that is in terms of the bearing capacity of the soil, that is CBR, then traffic loading in terms of million standard axles and climatic conditions. Some other other parameter associated with the pavement design are temperature, the moisture of the particular area, that particular soil, the pavement drainage, the material properties, especially the binder properties, that is bituminous or asphalt, and construction practices and maintenance. These are the factors we should be considered when we are designing the flexible pavement. So for what performance we have to design the flexible pavement? Should we go for functional performance, that is considering the riding quality, or structural performance in terms of strains or deflections? So for the road user, we expect functional performance. For the designer, we expect structural performance. But the pavement design which you try to do, that should serve the both adequate structural performance can be expected to give satisfactory functional performance as well. So not only the structural or functional, we have to give both the criteria into the consideration when we are designing the flexible pavement. The principles, design principles, we consider mechanistic empirical method, that is IRC 37 2013 mechanistic empirical method. Here performance is expressed in terms of stresses, strains and deflections using the linear elastic layer theory. So the term here linear elastic indicates when we remove the load, the pavement is going to be deflecting back or coming back to its original shape with the minimum strains. And also it is considered as a multi-layered system. Here the subgrade is considered to be semi-infinite, considering the new layer or existing subgrade, and all other layers are infinite in the horizontal extent. All other layers are GSB, then wet mix macadam, then DBM and BC layers. All are considered as the finite method. Other parameters we should consider, that is elastic modulus of all the layers, that we call as the resilient modulus here, and Poisson's ratio of all the layers and thickness of each layers. We have to give the input to calculate the stresses and strains and also deflections. So main design principles for the designing of a flexible pavement, we have to consider the location of the strains or the location of the failure points in the flexible pavement, so that we are trying to consider those into the design parameters. In this pavement design method, the vertical strain on top of the subgrade, here you can see here the subgrade, the strain at the top of the subgrade, that is below the wheel and at some distance from the wheel path. That position is considered as the critical location. So if you are going for some other layers like cement treated subbase or cement treated base, there also at the top of the cement treated subbase, we can have another critical point, there is a chances of occurring the crack, that is called as the critical points. The failure point, it's called as the critical points. Next, at the tensile strain at the top of the CTSB as well as bottom of the bituminous layer, that is the bottom of the DBM layer, that is considered as the fatigue strain, and top of the subgrade is called as a rutting strain. If you are going for a CTSB, additional strain need to be calculated at the top of the CTSB also. So these are the critical points or the critical locations for the designing of the pavement, that is rutting strain and fatigue strain. Now, if you are going for rutting criteria, because we are calculating the strains at the top of the subgrade and bottom of the bituminous layer, first we go for rutting criteria. Maximum rut depth is allowed as 20 mm. So with that, we can go for the calculation of this epsilon V, that is the vertical strain on top of the subgrade, with a reliability of 80% reliability. We will understand what is the meaning of the reliability also. So with this, knowing this NR stands for your million standard axles, MSA, and epsilon V, that is the vertical strain on top of the subgrade. So keeping this NR known, we have to calculate the allowable vertical strain on top of the subgrade. So for 90% reliability, NR is given by this equation. So what is the reliability meaning? So reliability means that if you are going for 90% reliability, the chances that the 10% of the area may be going for a failure. So if you are going for 80%, there is a chances that the area may go for 20%. If you are going for fatigue failure, that is at the top of the bottom of the bituminous layer, you can see here on the side of the photo, you can see this is the fatigue cracks. These are mainly developed at the bottom of the bituminous layer and propagated to top of the bituminous layer. So these fatigue cracks, the chances that if you are going for 80%, 20% failure chances and 90%, 10% failure chances. If you are going for rutting criteria, again 90% means there is a 10% road length maybe exceeds the maximum rut depth of 20 mm, and 80% means 20% exceeds the rut depth of 20 mm. These are the meaning of the reliability. So going for performance criteria for fatigue consideration, previous one we have considered the rutting criteria to calculate the epsilon V. Here we have to calculate the epsilon T, keeping the parameters like the constant C, and NF stands for your million standard axles in terms of MSA, and MRM stands for your resilient modulus of the bituminous material. So taking the factors, we have to calculate what is the epsilon T here. So for 80% reliability using this equation and 90% use this equation. So usually for the low volume roads, we go for 80% reliability, and high traffic intensity like expressways, national highways, we go for 90% reliability. So here the C stands constant, and VA stands for these are the Marshall mix design properties. We have to do the Marshall mix design property and find out this percentage of air voids and percentage of volume of effective bitumen in the mix. So these are the parameters we should use to calculate the value of M, and once you calculate the value of M, you can calculate C and put the C over here, and NF is known to you, calculate the epsilon T, that is fatigue strain at the bottom of the bituminous layers. These are the allowable fatigue strains depending upon the layer property we have considered. Now the analysis condition, the standard conditions considered for the design of flexible pavement, it is linear elastic model, that is the stress if you the elastic model is when you release the load, the pavement material remodeling back to its original shape. That is the purpose of the going for linear elastic model. And layers are fully bonded, and number of wheels considered as a dual wheels of each 20 kilonewton single wheel. Two wheels, each wheel carrying a 20 kilonewton. Contact pressure between the tire and the surface, it is called as 0.56 MPa. And the critical strains we are going to calculate that at the bottom of the bituminous layer. And if you are going for CTSB or cement treated base, tensile stress and strain at the bottom of the CTB, and subgrade, that is the rutting strain at the top of the subgrade. So these are the allowable strains we have to calculate using the equations given in the previous slides: fatigue cracking and rutting cracking. Now, typical cross section suggested by IRC 37 with the different the charts. You can go for different combinations of pavement design. Earlier it was only with one combination, that is subgrade, GSB and DBM and BC. Now it is allowed to free to select the any combination depending upon the loading condition, traffic loading condition, weather condition. So various parameters can be incorporated while designing the pavement. So here you can see here the conventional, the pavement where subgrade, GSB and DBM and BC. So here if you are going for this conventional the pavement with the normal combination, we have to calculate the strains at the top of the subgrade and bottom of the DBM layer, that is bottom of the bituminous layer. The various combinations are given by the IRC 37. You are free to select any combination. The first combination is the conventional pavement like subgrade, GSB, that is granular subbase, wet mix macadam and DBM BC. So if you are going for conventional pavement layers, you have to calculate the, that is rutting strain at the top of the subgrade, below the wheel path and away from the wheel path, and bottom of the bituminous layer we have to calculate this allowable strains. Now if your loading condition is very heavy, traffic is very heavy, then you can use CTSB. So purpose of going for CTB and CTSB, where the traffic is very heavy, you need more performance, more durability, prolonged life of the pavement, you have to go for CTSB or CTB. So here we try to use the cement or soil to stabilize this GSB or WMM. So that will treat as a cement treated base layer or cement treated sub-base layer. So once you are going for this cement treated base or sub-base layer, this will becomes like a semi-rigid pavement. So then there is a chances that the crack may be, the shrinkage crack may be developed at the CTB or CTSB. So to avoid that, the crack may develop at these layers and may prolong or propagate to the surface. To arrest that, we are going to introduce the crack relief layer, that is called as a SAMI or SAMI, that is stress absorbing membrane interlayer. So that will arrest the crack which are developed in the CTB or CTSB layer. The other combinations, the subgrade, CTSB, CTB, SAMI layer, that is stress absorbing membrane interlayer. Nowadays we have now the using of geosynthetic layer also chances that we are going to use as a SAMI layer. Then subgrade, omitting the CTB, we are going for cement treated subbase, and here the recycled asphalt. So pavement, we are going to use a recycled material in terms of in the layer of CTB, and again the bituminous layer, BC and DBM layer. Combinations are very different combinations. Then subgrade, CTSB, WMM and bituminous layer. This is the normal combination of our highways. So the sixth one, subgrade, GSB, CTB or granular crack relief layer or bituminous layers. So various combination, if you are going for CTB or CTSB, additional the strains we need to calculate. Otherwise, if you are going conventional pavement like WMM, GSB, only bottom of the top of the subgrade and bottom of the bituminous layer we have to calculate the allowable rutting strain and fatigue strain. These are the references I have used for preparing this presentation. In the next presentation, we will understand some more design parameters of flexible pavement and learn the various the steps involved in flexible pavement and solve one numerical example. Thank you.